Hello everyone, welcome back to this channel. Let's continue this course. As of now, we have completed a single neuron. We have understood how to create a deep neural network. Then we understood what is stochastic gradient descent, the loss function, the optimizer, and then how to prevent overfitting or underfitting. Okay, by using early stopping. Now today our lesson is about dropout and batch normalization. First we will read, then we will do the exercise. Okay. Let's read. There's more to the world of deep learning than just dense layers. There are dozens of kind of layer you might add to a model. We have learned how to implement dense layers in a neural network, but they are saying that other than dense layer, there are other types of layers exist. Okay. Some are like dense layers and define connection between neurons, and others can do pre-processing or transformer of other sorts. Okay. In this lesson, we will learn about two kinds of spatial layer, not containing any neurons themselves, but that add some functionality that can sometimes benefit a model in various ways. Both are commonly used in modern architecture. One is dropout. The first of this is the dropout layer, which can help correct overfitting. Overfitting, you remember, we studied in our last class. Overfitting means that the model is performing extremely well during training, but not on unseen data, not on testing data. Okay, why is that so? Because it is memorizing all the data points, like all the signals and all the random noises also. So it is memorizing every point. It has seen all the data. That's why it is performing good. It has cheated simply. You not cheated but memorized the thing. But when performing on the testing data, it has not seen the data. It has not captured the real meaning of the data, the real pattern of the data. So it is unable to perform. That is overfitting. Now here to prevent overfitting, we used early stopping. You remember. But another way is to use dropout layer. Okay. So in the last lesson, we talked about how overfitting is caused by the network learning spurious patterns in the training data. To recognize these patterns, a network will often rely on a very specific combination of weight, a kind of conspiracy. Okay, as every units are used every time, so what happens? They may make some conspiracy of weights. So being so specific, they tend to be fragile. Remove one and conspiracy falls apart. So if you remove this one, then this unit has to be dependent on other three. If you remove this one, then it has to be dependent on all these three. So what happens? The conspiracy breaks. Okay, this technique is known as dropout technique because here you are just removing one units. When? Which one? Then the answer is that randomly. Let's read this. To break up this conspiracy, we randomly drop out some fraction of layers input. Maybe at first epoch, I am randomly removing this two. Next epoch, I am randomly removing this two. Okay. So randomly, I am selecting some layers and I am dropping out. Dropping out means I am not using them. So the output from when it is removed, the output from this layer is not going to the next layer. Okay. So you understand that we are just making it stop. That I don't want any output from this layer. And we are selecting randomly. Why? So that the conspiracy falls apart. So that it doesn't think that this is the only way. So that it learns from this also, from different combinations, and it captures the real pattern rather than memorizing the thing. Okay, making it much harder for the network to learn those patterns in the training data. Instead, it has to search for broad patterns whose weight patterns tend to be more robust. Exactly. Now you have to find the general pattern. You can just memorize the thing. You have to understand the general pattern because sometimes it is stopped, sometimes it may be stopped randomly. Some neurons are stopped. Okay. If you have another layer also, after this also if you have one more hidden layer, then you can use dropout layer for these layers also. Okay. Anyway, you could also think about dropout as creating a kind of ensemble of networks. The predictions will no longer be made by one big network but instead by a committee of smaller networks. So what is happening? I am not using the big network always. I am taking some smaller networks each and every time. Different networks every time. Okay. So it will get different kind of output, different kind of pattern. So it will be able to get the generalized pattern. That means you are not taking the feedback from one person or the exact three persons always. What you are doing, you are randomly taking two persons or three persons or one persons, and you are taking the feedback so that you understand what is the general pattern. That is the simple logic. Individuals in the committee tend to make different kinds of mistakes, but we right at the same time, making the committee as a whole better than any individual. Okay. At the same time, you are not using everyone, but you are using more than one. You are not taking from any individual. You are taking from committee of smaller networks. Okay. Now adding dropout. In Keras, the dropout rate argument rate defines what percentage of the input units to startup. Put the dropout layer just before the layer you want the dropout applied to. So keras dot sequential layers dot dropout layers dot dense. That means when you are using this layers dot dropout rate equal to 0.3, it means that for the next layer apply 30% dropout. If you have 10 units in the next layer, then 3 units will be stopped every time. Random 3 units, no fixed. Maybe in the first epoch, first 3 units, maybe in the second epoch, other 3 units, like randomly. Same unit may also be selected, same unit may not be selected as well. It's like sampling. So randomly you are dropping out person in the next layer. Okay, so this is the way you can use the dropout. You have to just use the dropout function. Fine. Okay, so you have understood what is dropout, just dropping out some layer. Now our next concept is about batch normalization. The next special layer is batch normalization, or we can say batch norm. That is for when your training is slow or maybe unstable. For that you use batch normalization. What happens? Suppose in your data set you have different kind of columns. One is about height. So height may be 4 feet, maybe 3 feet, maybe 5 feet. One is about distance. That may be 150 miles, 200 miles. One more column is suppose about price, which may be 20 lakhs, 30 lakhs. So you understand that there are differences in numbers. One is 4, one is 2 lakh, one is 150. They are not in the same scale. So that may create a problem for your machine learning algorithm. Some features may get much priority over other features. They may dominate, but in reality, that may not be true. So, what we have to do, we have to bring them into a single common scale. Like maybe within 0 to 1, the minimum will be 0, the maximum will be 1, or any other minimum or maximum value. Any kind of scaling that depends on uh, how is your data set. You have to scale your data. Simple. So with neural network, it's good idea to put all your data on a common scale so that every feature gets the same priority. No feature can dominate other features. Features wins input. Perhaps with something like scikit-learn's standard scalar, min-max scalar. These are the libraries which are used for scaling the data set. Okay. The reason is that SGD, stochastic gradient descent, will shift the network weights in proportion to how large an activation the data produces. Features that tend to produce activations of very different sizes can make for unstable training behavior. Exactly, if different features have different kinds of data and they produce activations of different sizes, then it may be unstable for the training. So you have to scale it. Now, if it's good to normalize the data before it goes into the network, as you are using many layers, and if the output from this one, from any neuron, if they are not in the same scale, they may create a problem for the next layer. For this layer, they may be a problem. Okay, so maybe also normalizing inside the network would be better. So before giving the input, we are using this standard scaling or min max scaling. But inside the layer also we can scale the data so that the output from this layer gets normalized and then it goes as an input for the next layer. Because output from this layer is also input of this layer. Here we are doing the standard scaling normalization. Fine. But what if here if the output is not scaled? This is also input for this layer, right? So we also have to scale it here. That is what is batch normalization. We have a special kind of layer that can do this. That is batch normalization layer. A batch normalization layer looks at each batch as it comes in, first normalizing the batch with its own mean and standard deviation. That is a technique by using you can do the batch normalization, and then also putting the data on a new scale. Exactly, with two trainable scaling parameters. Batch norm, in effect, performs a kind of coordinated rescaling of its inputs. Fine. Most often, batch norm is added as an aid to the optimization process, though it can sometimes also help prediction performance. Models with batch norm tend to need fewer epochs to complete training. Moreover, batch norm can also fix various problems that can cause the training to get stuck. Consider adding batch normalization to your models, especially if you are having trouble during training. Adding batch normalization. It seems that batch normalization can be used at almost any point in a network. Like see, here I have used layers.dense, a dense layer, 16 units, ReLU activation function. Next, you apply batch normalization layer. Okay, so what happens? Whatever the output from this layer will be normalized, will be bring into a same scale, maybe using the mean and standard deviation. See, layers.den 16, you are doing the normalization. Okay, so this is a way by which you can do batch normalization, or you can use this also. Here you are just breaking this. Like first you are creating the dense layer, then you are applying the batch normalization, then you are passing it through the railway activation. And if you add it as the first layer of your network, it can act as a kind of adaptive preprocessor, like standard scaler. Okay, now example. Using dropout and batch normalization, they have developed a red wine model. Now we will increase the capacity even more, but add dropout to control overfitting and batch normalization to speed up optimization. Just go through the code. Okay, matplotlib downloaded, plot.style.use, and pandas. This is the data set, train, validation data, split the data, y train, y valid, everything is set. Now you use the dropout layer. So you may need to increase the number of units in the dense layer. First one we learned dropout layer. So keras, import layers. First the dense 1024 units, ReLU activation, input step equal to 11. Next layers dot dropout 0.3. That means 30% of the neurons will be dropped out. Fine. After that you apply batch normalization. It will be normalized by mean and standard deviation. Next, again another layer. So the normalized input output is going as an input for this layer. Again, you are dropping out some portions. You are using batch normalization. Next layer, you are using dropout. You are using batch normalization. Okay. There's nothing to change this time in how we set up the training. Obviously, you used before Adam and Amy, they have used that only. In the history, you are keeping model.fit, you are passing extend, ytrain, validation data, you are giving 256 batch size, randomly 256 data points will be taken, epochs 100 times, was 0, you are converting it into the data frame and you have plotted the loss. See, this is the loss and this is the validation loss. So you'll typically get better performance if you standardize your data before using it for training. That we are able to use the raw data at all, however, shows how effective batch normalization can be on more difficult data sets. See how it has performed so well at the end, right? This is due to the batch normalization. Now your turn, let's do it. In this exercise, you will add dropout to the Spotify model and see how normalization can let you successfully train model on difficult data set. Okay, let's understand. Same, just they have created the plots, and they have used that Spotify dataset we used earlier also. Let me run all these datasets. Then we have to add a dropout to the model. Okay, we will add a dropout, we will add a batch normalization. It's taking time. It's done. Okay, now let's run this. Here is the last model from exercise 4. Add two dropout layers, one after dense layer with 128 units and one after the dense layer with 64 units. And dropout 0.3, 30% dropout. Okay. So one after 128 units, one after 64 units. So simply you have to write layers dot dense, sorry, dropout, and inside that you have to mention 0.3, right? Same, you have to use 1 after 64. I've just copy pasted. Okay, now let's run this. I'm so sorry. Comma, comma. Now let's run this. Okay, just run it once. If you want, you can first take the hint. You don't need go. Dense dropout, dense dropout, dense. Exactly. Okay. Now run this next cell to train the model. See the effect of adding dropout. Same Adam optimizer, MAE loss function, history is taken, history is plotted. Same things. See, loss and validation loss. Performing well. If the validation loss is getting increased, then you can say it is overfitting. In this scenario, here it is underfitting. But you can see that here it's performing extremely well because loss and valid loss, both of them are getting reduced. Now, recall from the model tended to overfit the data around epoch 5. Did adding dropouts seem to help prevent overfitting? Yes, obviously. From the learning curves, you can see that the validation loss remains near a constant max minimum, even though the training loss continues to decrease. So we can see that adding dropout did prevent overfitting this time. Okay. Earlier it was not like that, it was overfitting. So moreover, by making it harder for the network to fit spurious patterns, dropout may have encouraged the network to seek out more of the true patterns. Exactly. So don't just learn the spurious patterns. Instead, use different kind of committee of smaller networks and try to find the true patterns. Okay, now we will switch topics to explore how batch normalization can fix problems in training. Load the concrete dataset. We won't do any standardization this time. This will make the batch normalization much more apparent. Just we have downloaded the dataset. We have not performed any standardization this time so that we can understand how batch normalization is having an impact. Just here we have downloaded the dataset and they have made a copy and it is dropped. Extern is set. Y train. Output is the compressive strength. So Y valid, X valid, Y valid. Input shape is also taken. Let's run. Okay, done. Next is run the following cell to train the network on unstandardized concrete data. Keras.sequential, dense layer, dense layer, dense layer, model.compile. Optimizer SGD is used here because this is more sensitive to differences of scale. Adam is not taken. Loss MAE. Matrices also MAE. History is plotted. So PD dot data frame history dot history. Same. It is let it run. See, you can find a blank graph. Did you end up with a blank graph? Trying to train this network on this data set will usually fail even when it does converge due to lucky weight initialization. That means if it even converges, it tends to converge to a very large number. So what is happening? Actually, it is getting failed, but even if it converges due to some good initialization, that lucky initialization, that may converge to a very large number. So that's why we are actually getting failed. Now we are going to use our techniques, which is batch normalization. Okay, now this problem can be solved by adding batch normalization layers. Batch normalization can help solve this problem. Okay, they have told you add 4 batch normalization layer, one before each of the dense layer. So you have to write layers dot batch normalization, and you have to pass the input. Okay, now remember to move the input shape argument to the new first layer. Okay, done it. So this one will be deleted. Next, again, you have to put the batch normalization layer, give a comma, and after that, put it here and after every dense layer. So maybe there also. Okay, but sorry, you have to put the comma. This is a class, right? Now let's run it. See, correct. Okay, run the next cell to see if it will let us train the model. Just okay. Now let's do this one. Evaluate batch normalization, optimizer SGD, loss MAE, matrices MAE, epochs 100, history. Let's plot it. See how it is performing after adding the batch normalization. Okay. See. Okay. Earlier it was completely blank because it was converging to a large number, or it may have failed, but this time it is working nice. Validation loss and the loss are close to nearby. So batch normalization is giving you. You can see that at batch normalization was a big improvement. By adaptively scaling the data as it passes through the network, batch normalization can let you train models on difficult data sets. Okay, so we have completed the task. So let's meet in our next class. Till then, bye. Happy learning.